Hi, I'm Christian and I'm going to demonstrate the DDS automotive example. The example domain encompasses a vehicle with simplified level 3 autonomous system combining sensor data to control the movement of the vehicle. The SysML model is created using real-life automotive MBSE design process. First, the system requirements were defined from which the rest of the model was derived. Based on the requirements, the use cases and activity diagrams were created, and the type system was made. The structural decomposition is designed using the aforementioned diagrams. Let's take a look at the system requirements. The requirements are arranged into multiple levels, with the top level ones being more abstract requirements, and the lower level ones being more specific subsystem requirements. The example has multiple tables displaying these levels separately, as well as a single table containing all the requirements. The folder structure also represents the requirement levels. The collision avoidance system is responsible of orchestrating safety-critical autonomous features based on the objects surrounding the vehicle. The sensors such as the LiDAR and the rear view cam are responsible for collecting data of the surroundings and forwarding it to the sensor fusion module for processing. The vision sensor processor processes raw cam image feed, forwarding it to the SFM, while the sensor fusion module publishes aggregated sensor information to the collision avoidance system. The vehicle platform requirements table contains the requirements of the vehicle's actuators and interfaces, such as the steering control unit, the electronic throttle control system, the electric hydraulic combination brake system, the human-machine interface for the displays, haptic feedback, and the vehicle control sensors. To make the example more lifelike, non-critical systems were also included, like the climate control system and stereo system. In addition to the system requirements, data transfer endpoint requirements were also defined. Let's check out the type system. Based on the requirements, the following types were created. The platform status and platform control used by the vehicle platform is here. Types for the driver alerts displayed on the HMI display can be seen here. The type of the raw cam image is shown here. If we scroll down, the pre-processed vision objects type is found here. Here we have the LiDAR data. And finally, the type for the fused sensor objects coming from the SFM can be found here. For the aforementioned types, DDS topics were created which provide connectivity between the system components. The behavior of the vehicle is defined via a use case diagram and many activity diagrams. Here you can see the use case diagram with the driver operating the vehicle. These use cases and activity diagrams are also organized in a table for easier visibility. There are three main use cases: the driving of the vehicle, such as braking, acceleration, and steering; using non-critical features such as the comfort features; and engaging autonomous features. The autonomous feature usage can be further decomposed into passive use cases, such as the blind spot monitoring and collision avoidance, and active use cases, such as automated parking and so on. For most use cases, activity diagrams are created decomposing the use cases into steps, linking back to the original requirements. Let's see the decomposition of the Engage Autonomous Features use case. Let's check the general collision avoidance step activity diagram. As you can see, it consists of the fusion of the vision data, the collision avoidance, and the display of possible warnings. The display warning activity is already linked to the HMI system component via a stream lane. Let's see what's inside the Create Sensor Object step activity. As you can see, the LiDAR and the cam data are fused together in this activity. The data merging is further decomposed by sub-activity. If we take a peek inside the sub-activity, we can see that the merging is done by the SFM. This is indicated by the swim lane. Merged data is then forwarded to the collision avoidance system. The collision avoidance system calculates possible collisions and engages the brake sequence if needed. From there, the brake system takes control. Based on the behavior and the type system, the structural decomposition can be created. We can see the BDD with the sensors, sensor processing, autonomy, comfort system, and vehicle platform, all contained by the vehicle. In the IBD diagram, we can see how the components communicate via the DDS data bus and work together to operate the vehicle. The sensors send data to the SFM, which provides data for the CAS. The CAS then controls the vehicle platform's subsystems if needed. We can assign different quality of service profiles for the DDS topics. Here we already have some profiles created. Some of these profiles are assigned to our endpoints. For example, the cam reader and writer ports currently both use the same cam image profile. Let's check the IBD once again. Here we can see the writer port and the reader port. We have a prepared working application based on the exported DDS model. Let's export the model via DDS export, see the system in action, and see how different quality of service profiles affect the system behavior. Let's double check what quality of service profile was used in the XML. This is the same profile what we've seen in the assignment table. Let's start up the system. We can see the running system communicating between the previously defined system components using the quality of service profiles. Keep in mind the bandwidth of the rear view cam and the rear view cam observer. For the purpose of this example, we are going to explore the following theoretical emergent scenario. We have received a report from the software development team that in the current configuration, the RCO is overloaded and can barely process the images at the current specified rate. In adherence to the company MBSE workflow, issues detected on the software level need to be reviewed and propagated through the system requirements. In our scenario, the HDMI requirements specify that the RCO needs to process data at 4.2 megabytes per second. To comply with the software team's suggestion, this will be changed to 0.56 megabytes per second. Since these requirements are directly traced to the DDS quality of service configurations, all changes made to the running example can be properly monitored. An additional added value of the DDS is that quality of service definitions can be configured on an endpoint level, meaning we can lower the data reception rate of the RCO, but keep the rates of the cam and the vision sensor intact. Let's change the quality of service profile of the rear view cam observer's reader port to a lower bandwidth profile and see what happens. I will check the XML for the quality of service profile. Notice how the lowered bandwidth of the rear view cam observer affects system performance.